In this lesson, we're going to talk about the properties of rational functions. So first we have a rational function as a function of the form r of x equals p of x over q of x, where p and q are polynomial functions, and q is not the zero polynomial because it's in the denominator. The domain of a rational function is a set of all real numbers, except those for which the denominator q is 0. So here in these first examples, we're going to find the domain of these rational functions. So it's all real numbers except for what the denominator cannot equal for it to be 0. And it is important when we're finding domain, we find domain before simplifying to lowest terms. Okay, so make sure we are finding the domain before we do any type of simplifying. All right, so first here, our denominator is x plus 5. So for that to not equal 0, that means x cannot equal -5. So you're going to see the notation written as your set notation most of the time here. So the domain is all real numbers x such that x cannot equal -5. Next we have x squared minus 4 cannot equal 0. So x squared cannot equal 4. Taking the square root of both sides, x cannot equal positive or -2. So domain is the set of all real numbers x such that x cannot equal -2, comma, +2. Looking at the denominator of x squared plus 1. X squared plus 1 cannot equal 0. X squared cannot equal -1. If I'm taking the square root, I get x cannot equal plus or minus square root of -1. But that is not a real number. Well, we already know the domain is a set of real numbers, so we know it can't be a non-real number. So for this one, we do not have any restrictions, and our domain is all real numbers. And last here, I'm not going to do any factoring to simplify first because I want to find the domain. So x minus 1 cannot equal 0. So x cannot equal 1. So our domain is all real numbers x such that x cannot equal 1. Moving on to using transformations to graph. So this is just like with any other transformations, except for now we get involved with some asymptotes, and those are these invisible lines that our graph is going to approach, but never, but it approaches that the asymptote, but it does not typically cross or intersect that, but it approaches it. So we got r of x equals 1 over x minus 2 quantity squared plus 1. Our domain is a set of all real numbers x such that x cannot equal 2. So that means that x equals 2, we have what's called a vertical asymptote. All right, and we're also going to have a horizontal asymptote at x equals 1, and we'll be talking about how we get that and where we get that from. But if I just focus on the transformations here, my original equation I'm looking at is y equals 1 over x squared. So a couple points on that graph would be 1, 1, and -1, 1. So if I perform the transformations, my transformations are right 2 and up 1. So if I do that, my new ordered pair would be 3, 2 and 1, 2. So I plot those points, 3, 2, 1, 2, our graph, something like this. So it's approaching those asymptotes, but never really touching or crossing. All right. So definition here of horizontal and vertical asymptotes. You can read that there, but those help tell us the end behavior. Okay, so a horizontal asymptote is going to be written as y equals L, where L is some limit that the graph is approaching. All right, so as x approaches infinity, then the function is approaching L, and then end behavior in this one is just showing as x is approaching negative infinity, then the function is approaching L. And then we have vertical asymptotes. Our equation is x equals c, so that line is x equals c. So as c approaches, as x approaches c from the left, then the function is approaching infinity, and as x approaches c from the right, then the function is approaching infinity. And then we also have a situation here where as x is approaching c from the left, then the function is approaching negative infinity, and as x is approaching c from the right of the asymptote, then the function is approaching positive infinity. We will be finding asymptotes using some algebra here, in an algebraic way. So the graph of a rational function in lowest terms, okay, that is important here. So when we are talking about asymptotes, we need our rational function to be in lowest terms. It has a vertical asymptote if x equals r is a real zero of the denominator. So for vertical asymptotes, we are looking at the denominator when our function is in its lowest terms. So if I look at example A here, I have x plus 3 over x minus 1. That is in lowest terms. It cannot be simplified. So I am looking at the denominator here and thinking, okay, what is the real zero of x minus 1? So I'm setting equal to 0. And I get x is 1. So that means x equals 1 is the vertical asymptote of graph f of our function there. Okay, r of x equals x over x squared minus 4. I need to make sure it's in lowest term. I'm going to go ahead and factor the denominator. So that's x over x minus 2 times x plus 2. It's the difference of perfect squares. None of my factors simplify there. So it is in lowest terms. So we are looking at our denominator. X minus 2 equals 0, x plus 2 equals 0. We get x equals 2, x equals negative 2. So both of those are vertical asymptotes of graph R. All right. Next here we have x squared over x squared plus 1. We cannot factor x squared plus 1, so it's in simplest terms. So I'm taking my x squared plus 1 and setting it equal to 0. We kind of already talked about this one. If I solve that, x squared equals negative 1, x equals plus or minus square root of negative 1. That is a non-real number, so there are no vertical asymptotes. Of graph H. And last here, we have x squared minus 9 over x squared plus 4x minus 21. We need to factor that because we need this in lowest terms. X squared minus 9 is a difference of perfect squares. Factoring the bottom. What multiplies to get negative 21 but adds to get 4 is a combination of 7 and 3. It would be minus 3 and positive 7. The factor of x minus 3 simplifies. So this is x plus 3 over x plus 7. When looking for the asymptotes, I'm looking at the denominator. So the real zeros of x plus 7 would be x equals negative 7. So x equals negative 7 is the vertical asymptote of g of x. All right, now moving on to horizontal and oblique asymptotes. So sometimes oblique asymptotes are referred to as a slant asymptote. So we have horizontal, vertical, and oblique. So horizontal and oblique, we are looking for the degrees of the numerator and denominator of the rational function, and we are going to compare them, and that will help us figure out how do we find the asymptote. So if the degree of the numerator is less than the degree of the denominator, then the line y equals 0, which is your x-axis, is a horizontal asymptote. So we have that. If n is equal to m, so if the degree of the numerator is the same as the degree of the denominator, then y equals a sub n over b sub n is the horizontal asymptote. That's just the ratio of the leading coefficients. Okay, so your leading coefficients there, that's what that is coming from. All right, if the degree of the numerator is 1 more than the degree of the denominator, then the line y equals ax plus b, which is just your slope-intercept form, is an oblique asymptote. And how we find that is by polynomial division. Okay, so we will be doing examples where you can see that. And if the degree of the numerator is 2 more than or more than that, than the denominator, then there are no horizontal or oblique asymptotes, and the end behavior of the graph just resembles the power function a sub n over b sub n times x sub n minus m. All right, so we will see different examples of all of these, and we will use those. Also note here that a rational function will never have both a horizontal and an oblique asymptote, but it could have neither. So it can't have both, but it could have none. All right, find a horizontal asymptote if one exists of the graph of r of x. So looking at r of x here, we are looking at their degrees. The numerator has a degree of 3. The denominator has a degree of 5. So the degree of the numerator is less than that of the denominator. So looking at our little chart here, if the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is the horizontal asymptote. So y equals 0 is the horizontal asymptote. Okay, next find the horizontal or oblique asymptote. We're looking at the degrees. So we have a degree of 4 and a degree of 3. So the degree of the numerator is 1 more than the degree of the denominator. So if I'm looking here, that would be my third bullet here. That means the line y equals ax plus b is an oblique asymptote, which is the quotient found using polynomial division. So we have to divide this. So we're going to take, we're taking the 3x to the 4th minus x squared. So we want to fill in the missing terms. we are dividing that by x cubed minus x squared plus 1. You can fill in for that missing term too if you want, but we'll just line up the like terms. So how long division works with polynomials here is we're trying to figure out what do we have to multiply x cubed by to get 3x to the 4th. So x cubed multiplied by what to get 3x to the 4th? That would be 3x. So I'm going to write 3x. I'm going to line it above its like term. And what I'm going to do is multiply all of this by 3x out here. So when I do that, 3x times x cubed is 3x to the 4th. Negative x squared times 3x would be negative 3x cubed. 1 times 3x would be plus 3x. Now, be careful because we are subtracting all of that. So 3x squared minus, or 3x to the 4th minus 3x to the 4th goes away. 0 minus negative 3x cubed is positive 3x cubed. Negative x squared minus 0 is just negative x squared. 0x minus 3x would be negative 3x. Bring down the 0. And we repeat the process. So now I'm trying to find what can I multiply x cubed by to get 3x cubed. Well, I would just have to multiply it by 3. So we put plus 3. Now we actually multiply all of it by 3. So when I do that, I would have 3x cubed minus 3x squared plus 3. We are subtracting all of that. All right, so when we do that, let's see if I can make this a little smaller. When we do that, I'm left with negative x squared minus negative 3 is positive 2x squared minus 3x. 0 minus 3 would be minus 3. So that would be our remainder. And I'm not too worried about that right now. I'm focused on my oblique asymptote, which is the 3x plus 3. So y equals 3x plus 3 is the oblique asymptote. Okay. Next example, find the horizontal or oblique asymptote if one exists of the graph. We're looking at the degrees. So we got a degree of 2 in the numerator, a degree of 2 in the denominator. Looking at our bullet points here, when they are equal, our second one, the line y equals a sub n over b sub n is the horizontal asymptote, which is the ratio of the leading coefficients. So y equals 8 over 4, it's coming from there, which equals 2. So y equals 2 is our horizontal asymptote. And then last here, we got 2x to the 5th, so that's a degree of 5. We have x cubed, so that's a degree of 3. So the degree of the numerator is 2 more than the degree of the denominator. That's our last bullet point here. So there are no horizontal or oblique asymptotes. The end behavior of the graph will resemble the power function. So no horizontal or oblique asymptotes. Our end behavior resembles, okay, the ratio, which would be 2 over 1, times x to the subtract the powers, 5 minus 3, that's 2x squared. So we're going to have approaching positive infinity on for both sides of the end behavior there. All right, and that is how algebraically we are finding horizontal, oblique, and vertical asymptotes as well as the domain.